Okay, this is Math E102, fourth lecture. I want to start with some announcements about next week's quiz. Last year, I attempted to write 40-minute quizzes, figuring that there was no need to blow the whistle. I let people work until it appeared that everyone had answers down to every question they could answer, and that took about an hour. So this year I'm just giving in, and we'll say the quiz will be the first hour, the lecture will be the second hour next week. If you're a fast worker, you may get done in 40 minutes or less, and you can go take a stroll around Cambridge for a while if you like. The quiz already exists because for those of you who are watching this video, you know that if you live outside the New England states, you have to go through the extension school. You'll have got an email about this to find yourself a proctor and arrange to take this at roughly the same time as the folks who are here in Cambridge. So I delivered a PDF file today. I can tell you, therefore, that, big surprise, there is one question that is sort of basic theory about sets and probability spaces and stuff where you have to prove a little something, maybe even prove something by induction. There is, of course, a question involving counting, could be bridge, could be Coker, could be Munchkins, but it will involve binomial coefficients. There is a question that involves unions and intersections of events and the like, and may give you a chance to use the inclusion-exclusion principle, may give you a chance to evaluate a probability in two rather independent ways and know you're right because you got the same answer both ways. And then there's one problem that smacks of infinity where you have to set up an infinite series, a geometric series, mind you, and sum it in order to calculate the probability of some event. I have a hunch that someone may get a perfect score on this. I think for some of you it will be a challenge, but I think it is definitely easier than some of the harder homework problems. Speaking of which, I apologize profusely for the last problem on today's problem set. I made a mistake in assigning a problem from a book without having worked it. I looked at it and I said, yeah, that's the obvious sequel to the preceding problems. And Jerry Rosen pointed out in an email quite recently that you have to interpret the problem with many, many more words than the authors put in. And let me be correct, Jerry. You managed to solve the problem by saying the deal is you have these R successive draws from the lottery, and no draw is consecutive with the previous one, and furthermore, no number is ever repeated.
That's right.
And given those assumptions, the problem is solvable, the solution that's given is correct, and the technique for solving it is a very minor generalization of the second technique that's presented in the book. But I'm going to ask Chris just to throw that one out and give some extra credit to Jerry and anyone else who figured out how to restate this so that it's solvable. So again, apologies for that. Tonight I want to get into conditional probability, which in my opinion is what makes this subject most highly entertaining. I will start with a few very simple examples, and for the quiz next week there will be one opportunity for you to show that you know the definition of conditional probability and can apply it in a simple case. The more systematic approaches that I'll be presenting later in tonight's lecture will help enlighten you on probability in general, but I'm going to hold those to the second quiz because they lend themselves to very nice exam questions, which next week's quiz doesn't have enough space for. So I want to start out now with topic number one on the outline. My biblical namesake, Paul at Lystra. And I should tell you, genesis of the Bayesian Bible. My church in Framingham, Massachusetts, is rather open-minded about science in religious education. So my first venture into this was an adult education course that I taught called What Every Christian Should Know About Quantum Mechanics. That was such a success that after chatting with a fellow parishioner of mine who tracks incoming ICBMs for a living and discovering we both basically were professionally involved with using Bayes' theorem, we decided to offer a little course called Faith, Probability, and Bayesian Inference, and this was my contribution to it. And anyone who wants to see more of this can just come out to Framingham during Advent when I have offered Theology, Thermodynamics, and Miracles. So what I did for this was to, the Reverend Bayes was claimed by his supporters actually to have proved the existence of God. He made no claims himself, but posthumously outrageous claims were made. He was, however, a theologian and a good probabilist, and I looked to see whether his principles could be applied to the Bible, and I decided that as it was written, it just wasn't precise enough. So in the Bayesian Bible, you have 4 examples of how the Bible would have to read in order for the principles I'm teaching in this course to be applied. And the first of these I concocted as an example that I think is very useful for teaching conditional probability to people who have no idea of the abstraction of probability whatever, because it's a 100% counting problem. So let me read this through verse by verse, and then we'll try to put the data on the board. Everything in bold type is actually from the Bible. The rest is my own fabrication. So the one that's actually from the Bible. And he, Paul, came also to Derbe and to Lystra. A disciple was there named Timothy, the son of a Jewish woman who was a believer, but his father was a Greek. Now, the inhabitants of Lystra numbered 2,000 Jews and 8,000 Greeks. So if we're thinking of events, we can think of picking one of these people at random, and the count of the number of cases that lead to the event G, the person is a Greek, is 8,000, and for the Jews I will use G sub C because of the implication that everyone here is either a Jew or a Greek. Now, among the Jews, half were believers, but among the Greeks, only 1 of every 4 was yet a believer. So now we have other events. Someone randomly selected is a believer or a non-believer. And if we're told that half are believers and half are not, we get a complete breakdown of the population of Lystra into Jewish believers, Jewish non-believers, Greek believers, and Greek non-believers. And Paul commanded Timothy to go out into the market of the city to assemble a group of believers and to choose one of them by lot to be bought to Paul. And choosing by lot, of course, shows up quite frequently in the Bible. Judas's replacement was in fact chosen by lot. So that provides a reasonable basis for saying we have equally likely alternatives. Timothy goes out to the market and selects one of these 3,000 folks at random. And Timothy did as he was commanded and returned to Paul with a believer, saying, "My chosen believer waits outside, but I know not whether he is a Jew or a Greek." Paul replied, "Of believers thus chosen, 2 of 3 will be Greeks." Timothy replied, "How can this be, seeing that the fraction of believers is higher among the Jews?" Now, this is the standard misunderstanding about conditional probability. Right here, you see that the probability that if someone is a Greek, that person is a believer, is only 1 in 4. And a lot of people jump to the conclusion that that's also the probability that if someone is a believer, that person will be a Greek. In fact, those 2 numbers are quite different, those 2 concepts are quite different, and that's what I want to introduce. And Paul said, "Bring the man to me, and we shall learn." And indeed the man was a Greek, named Nicholas. Both he and Timothy were astounded at Paul's wisdom and resolved to accompany him on his travels. And of course, this is a common human failing. Someone makes a prediction based on either good or bad estimates of probability. It works out right, and people are unreasonably impressed by the fact that this probability estimate has led to a correct outcome in one isolated case. But let's see how the reasoning goes. So we've got the individual outcomes. We've got 3,000 equally likely individual outcomes right here. And Paul is making this prediction that the person that Timothy has chosen is more likely to be a Greek than a Jew. And he's basing this on the fact that there are 200 what you might call successful outcomes. So on the basis of our simplest notion of probability, which has been around certainly for centuries and probably for millennia, Paul can say, now I'm going to write it formally, the conditional probability, given that the person that's been chosen is a believer, that person is a Greek, is the ratio of the 2,000 successful outcomes for believers, where Paul's guess is right because we've got a Greek, over the 3,000 total outcomes, or 2/3. We'll recast this shortly in terms of probabilities rather than counting, but I hope everyone can see this is a straight counting argument that leads to the correct answer. So in cases like this, again, you don't need any abstractions or axioms or probability functions or anything to reach the right conclusion.
I have a question about the
Yes.
notation. Isn't that slash supposed to be read as, what is it, Greek discount?
This means this is a vertical bar.
Oh, not...
yes, thank
okay,
you.
Very good.
Okay, so that would mean Greek but not a believer.
Yeah, right.
But this one, which shows up only following the probability symbol, means Greek given that it's a believer. And this is my first use of that symbol, so that's a reasonable misreading. But you'll be seeing a lot more of it. And I'm actually going to define it shortly, very soon. But I want to do one more example that's based on straight counting principles. So we'll go on to number 2 now, conditional 4 aces. And after learning a bit about Texas Hold'em poker from a couple of members of the class, I'm beginning to think that this may be far more relevant to the reason some people are taking this course than I had appreciated. So this is a simple example of a poker problem where some of the cards are face up. And here's how it works. We have a deck of cards, a stacked deck of cards as it turns out, and your opponent's hand is being dealt first, and the variant of poker you're playing is one where the first 2 cards are dealt face up and the remaining 3 cards face down. As I said, it was a stacked deck. So there's your opponent's hand consisting of 2 aces and 3 other cards. And you might, for example, be holding 4 kings or something like that, and you're really interested in making a good assessment of the probability that your opponent has 4 aces. And of course, you don't go to the standard table, which says there's only 48 ways of getting 4 aces. Because here you've got 2 aces showing, and it's not that hard. So I'm going to do this problem in 2 different ways. The first way I'm going to do it is very straightforwardly by counting. We'll consider the rest of these 3 cards. And then I will show you the standard way of computing conditional probability based on its official definition, which will actually give us the same answer, but after a surprisingly more complicated calculation. And this is the prototype for the problem that it's reasonable to put on next week's quiz. Something where you just have to know the definition of conditional probability in order to do the right counting. So what have we got? We got 2 aces showing, and 3 cards face down. And what we want to calculate, here comes that vertical bar again, is the probability that the opponent holds a hand of 4 aces given that the 2 cards out of 5 that we've seen are 2 aces. Well, this is reasonably straightforward to do. In fact, let's think about the 3 cards that are here. If the opponent has 4 aces, 2 of these cards have to be what? They have to be the 2 missing aces. And we're only concerned about the set of cards. The order doesn't matter. So how many sets of 3 cards are there that will fill out this hand of 4 aces? 2 of the cards are aces. How many choices are there for the last one?
2 times 48.
48, thank you, yes. So there are 48 choices for the 5th card. And how many ways are there of selecting these 3 cards out of the ones that remain after the 2 aces came off the top of the deck?
6.
How many choose how many?
50
choose 3. Thanks, Anna. So we got 48 divided by 50 choose 3. And since I'm going to calculate this in a different way, I want to simplify this a bit. 48 over 50 times 49 times 48 over 3 times 2 times 1. 48's obligingly cancel. And we have 6 over 50 times 49. A slightly more complicated one, which I'm actually not going to do by the more conventional method because it becomes so messy that way, but which we can do here, is we can ask, what is the probability, given the 2 aces that we've already seen, that the opponent has a full house? This, I think, is a good example of my divide and conquer counting principle, where if there are different alternatives, you count them each separately and add the results up. Could someone describe the 2 different ways that this pair of aces could turn into a full house? Yeah.
You could get 1 ace in a pair, or you could get 3 of a kind.
Very good. So you could either get 3 of a kind, poor blackboard planning. Let's move that down a bit. So you could get an extra 3 of a kind, or an ace plus a pair. Okay, let's work on this. For 3 of a kind, how many choices are there for the rank of the 3 of a kind?
12.
12. You could have, for example, 3 8s or 3 7s. You couldn't have 3 aces, so there are only 12 choices. And as far as the suit selection for the 3 of a kind, 4. And I'm going to write it as 4 choose 3 because that leads to cleaner notes. Okay, so that's the 3 of a kind situation with the rank and the suits. And for the pair, if we get a full house, how many choices are there for the ace that finishes off the full house? 2. In the example here, we could get either the ace of clubs or the ace of spades. And then we have to get a pair. How many choices for the rank of that pair? 12. And how many choices for the suit that get involved in the pair?
4 choose 2.
4 choose 2. And then in the denominator, we have, as before, our 50 choose 3. And this can be simplified. I'll write it down. It's 12 times 16 over 50 choose 3. So there are 2 examples of straightforward application of conditional probability. And really, given the way the situation is set up, these are not fundamentally different from anything we've considered before. But I do want to stress that sometimes this brute force approach leads to the correct answer more quickly than using formulas. Okay, now having done that, I want to be a little more formal about this. So this is topic number 3. Conditional probability. And if we weren't mathematicians, if we were philosophers or economists, we might say, well, conditional probability is the number you use to get the correct odds in this sort of situation, and we thought a lot about it and concluded that here is a good formula for calculating. So we could say our description, our definition is based on real-world considerations, and then we've done some applied mathematics to come up with a formula. We are not such people. We are pure mathematicians. And as pure mathematicians, we say this is a definition of conditional probability. The symbol P, A given B means the probability of A intersect B divided by the probability of B. There are folks who think that numbers thus calculated have applications in the real world. They are welcome to apply this definition, but as far as we're concerned, this is a definition, nothing more, nothing less. It's shorthand for a convenient ratio. Now, let's see how this works out. How would it apply to the biblical example? Well, Paul is interested in estimating the probability that this randomly chosen believer is a Greek, and he says, well, that's the ratio of the probability that Timothy has brought back a Greek believer to the probability that he's brought back a believer. So this is, again, basically the ratio of Greek believers to all believers. But if we put it in terms of probability, we reason like this. 4/5 of the population of this town are Greeks. And then, given that someone is a Greek, there's one chance in 4 that that individual qualifies as a believer in Paul's mind. So there's the probability of the intersection. And notice this already involves concepts of conditional probability. We're saying we've got the probability that the individual is a Greek multiplied by the conditional probability that that person is a believer, given that he or she is a Greek.
Well, in your notes, you define the probability of B as 0.3, which all correct. Since 3,000 of the 10,000 inhabitants, and then you say are Greek believers. It's not Greek, simply believers.
So that's a typo in the notes.
Yeah.
Could you put that in an email, Jay? I
Yeah.
will forget to fix it if I... Okay, so for the denominator, which is correctly calculated, though incorrectly stated, what we really have to do is add together the probability of a Greek believer plus the probability of a non-Greek believer. 1/5 of this population is Jewish, and half of them are believers. So in the numerator, we've got 1/5. In the denominator, we've got a 1/5 plus a 1/10, or 0.3. And the ratio is 2/3. So in this example, this definition leads us to exactly the same calculation that we did before. But that is not always so. And in fact, I was surprised how difficult it was to do this poker example by using the definition. So let me now clear this one off to make room. And I want to try doing the poker example in the same way. I'll get the same right answer, but only after some rather difficult thought. So the first step is easy. And my general advice, for which this is a bit of a counterexample, is whenever you see this, just mindlessly write down the definition and then start plugging things in. But here is where we have to stop and think. What on earth does this mean? Probability of 4 aces intersect 2 aces. Well, what it really means is that of the 5 cards which include 4 aces, the 2 that happen to be face up are both aces. So I'm going to stack the deck a little bit more to show you what I mean. Here is an equivalent way of playing this game. The deck was shuffled to start with, right? So we have to calculate the probability of the event that we have observed is a little too strong a word, that we would observe if we could see the face down cards too. We could play the game like this. 5 cards get dealt, and then the opponent is instructed to flip 2 of them over and happens to pick 2 aces. Everyone agree that's an equivalent situation. Instead of dealing 2 cards face up and then 3 cards face down, we could deal 5 cards, choose 2 of them at random to turn face up, and the probabilities are exactly the same. Well, the probability of getting 4 aces is something that we can perfectly easily look up. It is 48, strictly speaking, over 52 choose 5. That's going to cancel, so I'm writing it small. So that's the probability of a hand with 4 aces in it. Out of all the 52 choose 5 possible poker hands, there are 48 that have 4 aces and one of the other 48 missing cards. Now, given that my opponent holds 4 aces, picks a card at random and flips it, what's the probability the first card flipped is an ace? 4/5, right? Okay. Now he's got 4 cards left. What's the probability that the second card he flips is also an ace?
3/4.
3/4. So that's our numerator, which is the probability that our opponent holds 4 aces and the 2 cards he happened to turn up to show to the world are both aces. Everyone happy with that? Okay, now let's go for the denominator. The probability that the 2 cards that he flips up are aces. That's basically the probability that if you choose 2 cards at random out of the deck, they're both aces, right? And that is fairly easy to calculate. We've got 52 There are 4 choose 2 ways of picking 2 aces to flip up. How many pairs of cards can you get off the top of a deck? 52 choose 2. And if you work rather hard on this, you will discover that it's again equal to 6 over 49 times 50. I have the arithmetic in my notes, but it would overflow the rest of this board. You can check my arithmetic yourself if you like. So the definition again gives the correct answer, but you have to think about the problem rather differently, and you have to do a slightly messy calculation. Okay. Now I'm going on to topic number 4, which is independence of events. In the first lecture, I gave an implicit example of the independence of two events, which I believe were the Yankees won the AFC, the American League East, and the Iraqi Constitution was rejected in the referendum. And people gave the correct answer to my question, how do you estimate the probability, by saying, in that case, you can multiply the two things together because I don't really believe that any Iraqi is going to change his or her vote on the Constitution based on whether the Red Sox or the Yankees won the division. And what you were thinking if you said that was those are independent events, and what you had in mind is there's no causal connection between the two of them. So that's the informal view of independent events. If event A can't in any sense cause event B either to happen or not happen, you think of them as independent. That is not the definition that we're going to use. That's frequently a useful interpretation of this concept, but our definition is this. A and B are independent events if the probability of their intersection is equal to the product of their probabilities. This is the situation which we frequently believe to be the case, and if two events have this property, then we call them independent. Now, let me explain why this is closely related to the notion I don't really think any Iraqi is going to change a vote based on whether the Yankees or the Red Sox won. Let's calculate the probability of A given B for two independent events. Well, that's the probability of the intersection, probability of A intersect B, divided by the probability of B. And if the events are independent, that's the probability of A times the probability of B over the probability of B. We get some nice cancellation. And what this says is that if two events are independent, the probability of A given B is the same as the probability of B. In other words, knowing whether event B has occurred or not doesn't affect your estimate of the probability that event A occurred. And frequently, when events are assumed to be independent, it's with this criterion in mind. Now, there are two concepts that are closely related, easily confused, and as different as they can be, really. We've also talked about disjoint events. Disjoint events have the property that if one of them happens, the other one can't possibly happen. Is being disjoint the same as being independent?
No.
No. Can anyone give a simple example of two events that are disjoint and clearly not independent?
Any event and its complement.
Any event and its complement. So, for example, I flip this coin, okay? Event A is that it's a head. Event A complement is that it's a tail. Those are clearly disjoint events. What's your estimate at the moment of the probability that it's a head?
1/2.
1/2. Okay, now I look at it, it's a tail. Given that it's a tail, what's your estimate of the conditional probability given that it's a tail, that it's a head?
0.
0, okay? So Disjoint events are not independent events. In fact, they are generally about as far from independent as you can get. I should also warn you that there are cases where events are sort of accidentally independent, where the probabilities just work out so that this formula holds, and you think about the situation and you say, I can't see any particular reason that one of them doesn't influence the other in that case. Don't worry about it. This definition is what it says, and you don't have to look for any cause and effect. Sometimes there's cause and effect. Frequently, there isn't. Now, in order to work examples, we're going to have to come up with systematic ways of calculating probabilities. And a particularly useful special case of a general formula is my topic 5, which we're going on to, which I have called complementary events. Let me illustrate this with a Venn diagram. There's set B. There's its complement, B complement. Here is event A. And event A, as shown in the diagram, has a non-empty intersection with B. And basically, what I want to write down is a formula.
Wait, event A is in the circle or outside?
Sorry, event A is in the circle. Thanks, Jay. So event A is here, and I just want to formalize the notion that A can be written as the disjoint union of the piece that I've shaded in green and the piece that I've shaded in red. I will do this quite formally. The universal set, omega, is, of course, the union of B and its complement. Take any event and its complement, their disjoint union is the entire set. Either an event happens or it doesn't. A, I can write as the intersection of the universal set with A, because intersecting with the universal set, the event that always happens, does nothing to any event. And then I can distribute that over B and B complement to say this is B intersect A union B complement intersect A. And this is, again, a disjoint union. And if you look at the Venn diagram, it proves nothing, but it's oh so helpful. What this is saying is that the event A is the disjoint union of two parts, A intersect B here and A intersect B complement here. And then our general formula is that the probability of event A, since event A is a disjoint union, is the probability of A intersect B plus the probability of A intersect B complement. And the form in which this is going to be especially useful to us is this. Just by definition, I can write this as the probability of A given B times the probability of B plus the probability of A given B complement times the probability of B complement. And you bought that argument informally already in the form of the probability of being a believer is the probability of being a Jew times the conditional probability that a Jew is a believer plus the probability of being a Greek times the conditional probability that a Greek is a believer. So this is just formalizing a notion that people reasonably intuitively use to calculate probabilities, but we're going to use it over and over again in doing examples. Now for my favorite example. We live in a politically correct country, and therefore many events are sort of taboo, and I've decided, since I have a beard, an event that I don't have to regard as taboo is the event the male in question is bearded. So here is the storyline for the bearded man problem. This is partly inspired by the fact that one of my best ever extension math students was the public defender who defended Richard Reed, the shoe bomber. So you know, whenever we go through airports, we have to take off our shoes and they get scanned, and they might have explosives in them. And you've also read these signs about airports you're advised to stay away from because the State Department thinks they're especially dangerous. I've never been to any of these, but I think this story has to be set in one of them because of the numbers I'm using. So the story is this. There's a single mom working in an airport as a security screener. She gets paid a pittance as a regular wage, not really enough to put food on the table for her family. But every time she catches a man trying to get on a plane with explosives in her shoes, she collects a hefty bonus. So she has an incentive to catch people with explosives in their shoes, and being a bright young lady, she keeps careful statistics and comes up with some estimates of probabilities and conditional probabilities that she believes are pretty good. So here are the events for this bearded man problem. Hope it became clear that I was switching to this topic. So event A is that a male passenger chosen at random has explosive shoes. And event B is that the male passenger in question sports a beard. And here are some probability estimates that our hypothetical security screener might come up with. As I say, I wouldn't want to fly out of this airport, but let's assume that 2/10 of the male passengers have explosives in their shoes, which means that 8/10 of them don't. And then, on the basis of observation, she has noticed that if someone has explosives in his shoes, the probability that that person has a beard is 0.6%, while of the passengers that are wearing non-explosive shoes, the percentage of beards is much smaller, only about 5%.
The first one is bearded and has explosives, and is bearded.
No. This is saying, given that someone has explosive shoes, the probability that that person has a beard is 0.6. And this might mean that during the past couple of years, she's found 1,000 people with explosives in their shoes and noticed that 600 of them had beards. And that's a reasonable basis for estimating this probability is 0.6, whereas the number of people with no explosives in their shoes, those folks tended to be much more likely to be clean-shaven. Okay, so here, of course, is the problem. Two men are sauntering up to the inspection station. She only has the opportunity to inspect one of them. One of these folks has a beard. The other doesn't have a beard. She doesn't know where the grocery money is coming from. Which person should she choose to inspect? And so she does a little conditional probability analysis and mentally turns this into a table, which is what I recommend you do when faced with such a problem. We've got beard, no beard, explosives, no explosives, and our goal is to fill in this table in such a way that in every box of the table, we have the probability of the intersection of the two events in question. And since these 4 intersections cover all 4 possibilities, those are going to sum to 1. And we can do this quite easily from these numbers. The probability that someone has explosive shoes is 0.2. Given this, what's the probability that someone has explosive shoes and is sporting a beard? Let me restate this question so you understand how simple it is. You grab someone at random knowing nothing, just someone heading into the airport. What's the probability that the person you grab has both explosive shoes and a beard? The probability of A intersect B. No. 0.12. Because it's the probability of having explosive shoes multiplied by the conditional probability that someone who has explosive shoes is sporting a beard. I'm just using the definition of conditional probability. When we say we accept this number, basically we're saying that means that this calculation is the product of this and that. And what's the probability that someone has explosive shoes and is clean shaven? 0.08. 0.08. Okay. Now we got the 80% of people who don't have explosive shoes. What's the probability that one of them has a beard? Sorry, I said that wrong. What is the probability that a randomly chosen male traveler in this airport has non-explosive shoes but happens to have a beard? 0.04. Obtained by taking this 0.8 and multiplying by the conditional probability that an explosiveless passenger has a beard. And what's the probability that you find someone who has no explosives and no beard? 0.76. So, given this sort of information for 2 events, the probability of one of the events and the conditional probability of the other event, given your chosen event and its complement, you can always fill out a table like this. This is complete information. Now, what does the screener say? She says, I want to interview the traveler who has the highest probability of having explosive shoes. So let me calculate the conditional probability, given that someone has a beard, that that person has explosive shoes. That's the right number. Everyone agree with me? What is this? This is the probability of A intersect B over the probability of B. What's the probability of A intersect B from our table? 0.12. And what's the probability of B? 0.16. You add this column. So we have enough information to calculate the probability of B and B complement. So she says, if I interview the person with the beard, the chance of finding someone with explosive shoes is 3/4. That's pretty good odds. If I pick the other person, the odds are pretty feeble. Well, you might think this is a happy ending. What actually happened, of course, was she did this. She was hauled in for facial hair profiling and fired. But this is, I did promise in the course description applications to national security, and this is one of them. And this is a nice example of a very generic type of problem. You can make hundreds of storylines up that work exactly the same way. And in every case, work out a table like this, and you get the right answer. And this is, in my opinion, probably the single most useful thing to know how to do with probability, because it's easy and most folks can't do it quite right. And the Reverend Bayes became quite famous basically for inventing this idea. Before we take a break, I've got 10 more minutes, do I? I got 10 more minutes to talk about lemons. This is an example from the textbook that shows that this sort of analysis can be extended to situations that are bigger than 2 by 2, and so we have a company that has manufacturing plants in 3 factory towns named Farad, Gilbert, and Henry. What do all these have in common, anyone?
They're all scientists, physicists who work at electromagnetism.
Yeah, they're all physicists who worked on electromagnetism. In fact, Farad is actually Faraday is the unit of capacitance, and Henry is also an electrical unit. I'm not sure that there's a unit called the Gilbert, but Gilbert was another pioneer in this subject. So it turns out that some of these towns have better quality control than others, and this is actually stated as a counting problem. Farad made 1,000 cars, and quality control is really bad. 20% of them are defective. In Gilbert, 2,000 cars were manufactured, and only 10% were defective. And finally, in Henry, 3,000 cars were manufactured, of which only 5% were defective. So on the basis of that, we can fill in a table showing the probabilities of lots of different events where D means defective. For example, the probability of the event F intersect D, the car was made in Farad and was defective, is 1/6, for the fact that 1/6 of the cars were made in Farad, multiplied by 1/5 for the conditional probability that a car manufactured in Farad is defective. Notice all these are really conditional probabilities. They're numbers that only apply given some other event. This one is 1/3 times 1/10, and this one is 1/2 because half the cars are made in Henry, and only 1 in 20 of them is defective. We can fill in the bottom row also, though we scarcely need it. 1/6 times 4/5, 1/3 times 9/10, and 1/2 times 19/20. And now Sturzacher comes up with a number of interesting questions you can ask. You can ask many more questions when you've got 6 numbers rather than 4, like you pick up your car and you hopefully ask the dealer, was this car made in Henry? And the dealer said, sorry, I don't know exactly where it was made, but I know for sure it wasn't made in Henry. And you start asking yourself, goodness, what is the conditional probability, given that my car wasn't manufactured in Henry, that it was manufactured in Farad? The obvious answer is 1/3, and that's what calculation will give us, because that's the probability of the event Farad and not Henry divided by the probability of not Henry. Now, this happens quite frequently when you're analyzing this sort of situation. This is a stupid-looking event. Farad intersect non-Henry. What's a simpler way of writing that? It's just the probability that it was made in Farad, because if it was made in Farad, of course it wasn't made in Henry. So this is just the probability of made in Farad over the probability of not made in Henry, and that turns out to be 1/6 divided by 1/2, or 1/3. So this shows the formulas are giving us the obvious answers. I think I've got 5 minutes still for the remaining ones. I'm just going to make it then. So the next question you ask yourself is, given that my car was not made in this wonderfully careful plant in Henry, what is the probability that I have bought a lemon? So let's formalize that. What is the probability of event D, my car is defective, given event H complement, the car wasn't manufactured in Henry? This is, of course, the probability of D intersect H complement divided by the probability of H complement. The probability of H complement, we know, is 1/2. What's the numerator? What do we have to add together to get the probability of this event? Well, we could have a Farad lemon or we could have a Gilbert lemon, right? So it's 1/30 plus 1/30 or 2/15. Basically, we look at all the cars that weren't made in Henry and just ask what fraction of them were defective. In the textbook, this is done entirely in terms of counting, but I thought I'd do it in terms of probability. The analysis is entirely equivalent. The numbers in the book are the numbers I'm using multiplied by 6,000, but I thought you might as well see it both ways. Okay, the last pair of questions. What's the probability that I bought a lemon? Well, the probability that I've bought a lemon is the sum of the probabilities that I bought a lemon made in Farad, a lemon made in Gilbert, and a lemon made in Henry. So this is 1/30 from here plus another 30th from here plus 1/40 from here. And when you add that up, you get 11/120. This is going to be the denominator in our conditional probability calculation. And usually when you do these conditional probability calculations, working out the denominator is the most tedious part of the calculation, because now we can answer the last question fairly easily. You drive the car away, and after 5 miles it's shut down. It's towed into the dealer. It's repaired. It goes 10 miles and breaks down. And you reluctantly conclude that you have bought a lemon, and you ask yourself, what is the probability, given that this car has turned out to be defective, that it was made in Farad? Now that one isn't really obvious, is it? You say Farad makes a lot of bad cars, so it seems reasonable that a defective car came from Farad, but to answer it right, you have to use conditional probability. Probability made in Farad given defective is the probability that a car is a defective Farad car divided by the probability that it's a defective car. What's the numerator of this? 1/30 over 11/120, which is 4/11. And if you want to do this in a more simple way, you just add up the number of defective cars and figure out what fraction of them were made in Farad. So it's not really that subtle. Okay, let's take a short break and rev up the tape for another hour. Thank you, Katie. And following the book's notation, I'm going to write it just as the union over I of B sub I. This leaves open the possibility that it's a union of an infinite number of events, but it could also be a finite number of events. And then I can say event A can be written as the union over I of A intersected with each of these events. That's disjoint. That's disjoint. I always like to keep noting when I have a disjoint union of events, because in that case I have this super simple formula that the probability of the union is the sum of the probabilities. And that's what I'm going to say. Now, the probability of event A can therefore be calculated in the following way, of which you have seen a couple of special case examples already. It's the sum over I of the probability of A intersect B sub I. And frequently when you go to calculate this, you calculate it as the probability of A given B sub I times the probability of B sub I. This works for an arbitrary union of events, but there's really nothing new to it. This is like probability of explosive shoes times the probability of bearded given explosive shoes plus the probability of non-explosive shoes multiplied by the probability of bearded given non-explosive shoes. All I'm saying here is that what we have been using so far for a union of two disjoint events, some event and its complement, applies equally when we have a union of any finite number or even an infinite number of disjoint events. Now, because these two things are in the same section of the book, I will take the opportunity to talk about the false positives issue. This is a very famous medical example of Bayesian inference. And what makes this example interesting is the numbers that I'm going to throw into it. But you will see cases like this described in the newspaper from time to time, and they are generally not well understood by the general public. So you will be more informed by most. So here's the idea. There's a very rare disease. And I will denote by event D, the event that an individual has the disease, but only one person in 100,000 has this disease. Now, one of our leading pharmaceutical companies, the folks who say, have you asked your doctor about this, have you asked your doctor about that, and so on, has created a pretty good test for this disease. And it's pretty good in the following sense, that if you actually have the disease, the probability of event F, that the test runs up a red flag and says you probably got this disease, that probability is 95%. So if someone has this rare disease and you give them this test, there's a 95% probability that it will come up with an indication that this disease is present. And when people come up with tests like this, people are always asking, why isn't the government spending more money for such and such? Why aren't we screening all our kids for this? And so on. And here's why. This test gives an occasional false positive. So my number, taken straight from the textbook, is that in the event you don't have this disease, there is still a 0.5% chance that the test comes up positive. You say, 0.5%? How could 0.5% possibly make any difference? We ought to be taking tax money out of our schools and using it to screen for this disease. We are neglecting the nation's health. Well, let's think about this from a more personal point of view. You go to your doctor. The doctor says, well, the government has ruled we have to run 457 laboratory tests on you for this year's physical. And when you come back, say, bad news, the test for this disease came up positive. Oh, horrors, horrors. And if you really got this disease, well, you better get your affairs in order. And then you go back and think about it in terms of conditional probability. Because the question that matters to you is what's this conditional probability? What's the conditional probability given that the test came out positive that I actually have this disease? And lots of people, all of whom would be wrong, would say, yeah, what's the order matter? If this disease has if this test has a 95% chance of catching the disease, the chance that the test comes up positive, you got the disease, is 95%. What are you asking stupid questions about? But nothing could be further from the truth. Let's do this right. This is the probability of D intersect F divided by the probability of F, which is basically saying, let's take all the cases where the test comes up positive and ask in what fraction of those cases is it a result of the person actually having the disease. And I will use the formula that I just derived in a very special case. This numerator is yet again the probability that you have the disease times the probability that the test comes up positive, given that you've got the disease, plus that same number onto which we must add the probability that you don't in fact have the disease, but the test came up positive nonetheless, that you got a false positive. Everyone happy with this? It's the same problem, a different storyline. And the interesting thing about this one is you can get a pretty good estimate of the answer by throwing away some of the numbers. So in the numerator, we have 10 to the minus 5, the probability that you've got the disease, multiplied by 0.95 for the test coming up positive. And in the denominator, we've got the same thing, plus the probability that you don't have the disease, 1 minus 10 to the minus 5, multiplied by 0.005. And I would say, for purposes of approximation, that it's certainly reasonable to ignore that. And it's also reasonable to ignore this. Because the overwhelming fraction of the positive results from this test are going to come from the overwhelming majority of people that don't have the disease for which the test yields a false positive. So a good estimate of the answer is 0.95 times 10 to the minus 5 divided by 5 times 10 to the minus 3, which is 0.19 times 10 to the minus 2, or 0.19%. In other words, if this test comes up positive on you, the probability that you actually have the disease is about 0.2%, and it doesn't really make sense to go out and seek treatment if the probability that you have it is that small, probably not even worth a follow-up test. So I have the understanding that there are a fair number of cases like this in medicine, where if you are designing tests for really rare things, even a very modest false alarm rate will make it a fruitless exercise to do screening of the general population, because the false positives will dominate the situation. Now we move to my two favorite problems, conditional Munchkins and Monty Hall. So let's do conditional Munchkins first. Let me remind you of the original Munchkin problem. In the original Munchkin problem, we had 4 plain Munchkins simulated by cookies and 2 chocolate Munchkins simulated by cookies. And my daughter puts 3 of them in a bag for Catherine, and the other 3 in a bag for Thomas. And Thomas contemplates his bag, estimating the probability that he has 0, 1, for 2 chocolate munchkins. And as I recall, the previous answer was the probability that he has 2 chocolate munchkins is 1/5. The probability that he has 1 chocolate munchkin is 3/5. And the probability that he has no chocolate munchkins is also 1/5. Now we're going to turn this into a conditional probability problem. And I should warn you, this style of question makes a great exam problem because it tests all sorts of things. So if it doesn't show up next week, it'll probably make it onto the final. So here's what happens. Catherine reaches into her bag. And like little Black Horner, she pulls out not a plum, but a munchkin, chosen at random. And it's a plain one. Okay, now put yourself in Thomas's position. Thomas says, I had estimates of the probability for having 0, 1, and 2 chocolate munchkins, but now that my sister has revealed a plain munchkin, I've got to up those estimates. There's now a higher probability that I have 1 or 2 chocolate munchkins, probably a lower probability that I have 0 chocolate munchkins, so I better redo my calculation. What I'm interested in knowing now is the following. Given that event B is that Catherine pulls out a plain munchkin, what Thomas now wants to estimate is, for example, the probability of A2 given B. Everyone happy with that as the relevant conditional probability for this problem? So let's do it. Let's do it systematically. Systematic way to do it is we have to calculate the probability of A2 intersect B and divide by the probability of B. Now, in the previous examples, I've said 2 or 3 times, the painful part of the calculation is working out this denominator. You have to add lots of things together. But this is a case where you can get the denominator without any calculation. And I want you to think about this very carefully, because this is a little bit like that 4 aces problem that I did at the start of the lecture. Frequently, there's a bunch of things going on. They're all random, and the net effect of them all is you pick something at random. So let's think about what went on. Lisa took the 6 munchkins. She took 3 at random and put them into Catherine's bag. Catherine then picked one of those 3 munchkins at random. That is no different from Catherine reaching into the original bag and grabbing one of the 6 munchkins. Everyone comfortable with that? And therefore, given that there are 4 plain munchkins and 2 chocolate ones, what's the probability of event B? 2/3. There are harder ways to get the number, but they all come out to 2/3 if you do them right. Okay, now the numerator is a little bit trickier. Let's draw a diagram for this situation. Suppose that Thomas really does have 2 chocolate munchkins. So the event is A2 intersect B, which means both the chocolate munchkins are in Thomas's bag, and when Catherine goes to grab one, the one she pulls out is plain. What's the conditional probability in this case that Catherine will pull out a plain munchkin? 1, because she's got nothing but plain munchkins in her bag. So in this case, we've got 1/5, which we calculated last time, times 1, and this works out to 3/10. Now, when I get started down this road, I say, that sounds right to me, but I want to be sure. I'm going to work out all 3 conditional probabilities and make sure they add to 1. So let's try another, because the other 2 are actually a little bit harder. Conditional probability of A1 given B? Well, of course, that's the probability of A1 intersect B divided by the probability of B. And the diagram in this case looks like this. There's Thomas's bag. There's Catherine's bag. The 2/3 still works in the denominator. The probability that Thomas has one Munchkin in his bag, which I calculated before, is 3/5. What's the probability that Catherine, in this circumstance, pulls a plain rather than a chocolate Munchkin out of her bag? 2/3. So remarkably, nothing changed. This is 6/10. Okay. Now, if we've done everything right, the probability that Thomas has no chocolate Munchkins has gone down to 1/10, but let's do it directly. So the probability, wow, the probability of the event A0 conditioned on B is, of course, the probability of A0 intersect B over the probability of B. The probability of A0 we worked out before. It's 1/5. And the diagram looks like this. Thomas has no chocolate Munchkins. Catherine has both of them. Under these circumstances, what's the conditional probability of event B given event A0? 1/3, right? 1/5 times 1/3 divided by 2/3. We get 1/10, and lo and behold, 3/10 plus 6/10 plus 1/10 equals 1. Now, that is not the only way to do this problem. It's the only way that I had thought of, but one of my students found a somewhat shorter way to do this problem, reasoning as follows. We get exactly the same setup if Catherine reaches into the original Munchkin bag, pulls out a Munchkin at random, and holds it in her hand while Lisa stuffs the bags with 2 other Munchkins for her and 3 for Thomas. Which means that Thomas can also answer these questions by saying, let's forget about the plain Munchkin that Catherine has and has taken a nibble out of. Let's just say there are 5 Munchkins, 2 of them are chocolate, I get 3 and she gets 2. So let's try doing the problem that way. It should lead to exactly the same answer with no explicit conditional probability reasoning. So this is another way. We have 5 Munchkins. Three plain, 2 chocolate, 3 for Thomas. What's the probability that he gets both the chocolate Munchkins? Well, let's do the denominator first. How many ways are there of selecting the Munchkins that go into Thomas's bag? 5 choose 3. And how many ways are there of selecting for Thomas both the chocolate Munchkins and 1 plain Munchkin? 3, right? Because you got 3 choices for the plain Munchkin he gets in addition to both the chocolate ones. That's 3 divided by 5 times 4 times 3 over 3 times 2 times 1, or 3/10, which agrees with the answer I just got from the conditional probability calculation. So that's another way of doing this sort of problem. And I guess if there's a general lesson in it, it's that from time to time with these problems, if you think about a different procedure for achieving the desired setup, you can get the right answer with a simpler calculation. Now we go to the Monty Hall problem. And this comes from a TV show, which I've never seen, called Let's Make a Deal. Has anyone here ever seen Let's Make a Deal? Sue has. Okay. As I understand it, here's how this worked out. There was a game show host named Monty Hall. There were 3 doors on the stage. Behind one of the doors was a shiny new car, and behind the other doors there were goats. Is that really so? They had real live goats?
No, but similar.
Okay, but booby prizes of some sort. And we assume that the car and the goats were arranged randomly behind the doors. That is, that any permutation of these 3 objects behind the 3 doors was equally likely. Otherwise, the game show would be cheating. So a contestant would come up, and Monty Hall would say, pick your lucky door, and if it turns out to have the car behind it, you win the car. Otherwise, you win the goat if that's what's behind it. And then to make the game interesting, Monty Hall would say, and you might want to see what one of these goats looks like, and rip open another door, guaranteed to reveal a goat. Now, in the textbook, this is under the heading of protocols, because in order to solve this problem correctly, you have to understand precisely the rules by which Monty Hall plays. Under no circumstance can Monty Hall open the door that the contestant has chosen. Under no circumstances can Monty Hall open the door that has the car behind it. What he has to do is open a door that the customer doesn't have, that the contestant hasn't chosen, and he has to reveal a goat in doing this. It is believed in the original version of the game that he picked at random, but another equally good way of doing this is to say there's a large goat and a small goat, and he always reveals the smallest goat that's available. So if he has a choice of goats, he reveals the smaller of the 2 goats. And then he says to the contestant, would you like to switch? And I gather some contestants did, some contestants didn't. And there was a raging debate about whether it was right to switch, with some people saying it was, and some people saying, look, there are 2 doors left, the 50-50 chance, it really doesn't make any difference. This was picked up by Parade magazine in the column written by Marilyn Vos-Savant, the world's smartest person, and she got it right, but I guess she got mail from thousands of PhDs who said she was wrong. And the charitable interpretation is that she hadn't stated the protocol clearly enough, and these people misunderstood the protocol. But a hunch is several thousand PhDs actually didn't know probability theory well enough to get this right. So we're going to try this. Okay, so someone who signed a release, will you come up here and be the contestant? First night, some of you signed something saying you were willing to be videoed. Good. Robert, you can come up here, and we'll do it over here. Now, what we have are pictures of U.S. presidents in here. One of these envelopes contains a picture of the first president, George Washington, on a $1 bill, in fact. The other 2 contain pictures of the most recent president, which I got off a website. And so the first thing for you to do is to pick one of these envelopes. Okay. Now, I'm Monty Hall. I have secret codes on these, and if I can remember the secret codes, let me look at yours. I just want to see the secret code. Yeah. So I have a secret code, so I know which of these have Washington and which have Bush, and I also have a criterion for selecting the larger of the two Bush photographs in the case where I have a choice. So using those criterion, I may not have had to use the second criterion. I rip this open and say, yes, indeed. And here we have a photograph of George Bush with a number of Iraqi Fulbright scholars. And now I ask, would you like to swap envelopes before you open?
No.
No. Okay, rip it open and see. And this always happens. Now, I'm going to prove to you that Robert made the wrong decision, that he settled for one chance in three when he could have had two chances in three, but nonetheless, the dollar is yours to keep. And the most interesting thing is, I did this in the same way for the Quincy House Senior Common Room, a mathematically challenged group. And exactly the same thing happened. My contestant made the provably wrong decision, got the dollar bill, and then I asked someone else to do it. And they did it wrong again. And I said, look, I just proved you double your odds of winning if you switch. Why did you open the envelope? He said, well, that's what Amy did, and she got the dollar, didn't she? And it turns out that people who study the psychology of probability have identified this as one of the things that people habitually do wrong. They attach inordinate weight in making probability estimates to the last example that occurred. So now I want to show you how to do this right. And we know how to do these things right. First, we identify a set of outcomes that we have reason to believe are equally likely, and we work from there. And in the case where the two goats are distinguishable, large and small, I will now reveal my answer. There were two-digit codes on the envelopes. The one with George Washington had a prime number on it. The other two had composite numbers, and the larger photograph was in the envelope with the larger of the two composite numbers. So I just had to quickly factor the two envelopes I had. As soon as I factored them both, I knew that Robert had the dollar bill, but I didn't let that on. And I opened the one with the larger code, 63, rather than the smaller one, 48. But I could have picked one or the other at random, and it wouldn't have made a difference. So we got 6 equally likely outcomes. We've got door 1, 2, and 3, and case 1, 2, 3, 4, 5, 6. And our assumption is that all permutations of the three objects are equally likely. So we've got car, small goat, car, large goat, small goat, car, large goat, car, small goat, large goat, car, large goat, small goat, car. And if the network is playing fair with this game show, each of these should be equally likely when the game starts. If you don't accept that, you've got no business doing probabilistic reasoning about this. And the fallacy, the way people get it wrong, once you understand this problem, it's awfully hard to understand how people get it wrong. But I think what they do is they say, well, it boils down to two choices. Either Robert can switch or he can't switch. And if you don't know which one is right, you assume they're equally likely. That's what probability theory is all about. And therefore, it's 50-50. It doesn't make any difference. And that's wrong because, as you will see in a minute, once it gets down to the choice, those two are not equally likely. Here are the equally likely alternatives. So let's interpret the rules. Monty opens which door? He's going to reveal the smaller goat, G1, if he has a choice. So what's he going to open here?
Which one is the smaller?
The smaller one, G1, is small and G2 is large. So which door will he choose to open here? 2. And here? He's going to open the door that reveals the smaller goat. And in this case, he's going to open 3. In this case, he's going to open... No, he can't open 1 because Robert chose door 1. He's going to open 3 because that's the only one that has a goat behind it. And here he's going to open 3. And here he's going to open 2. And here he's going to open 2.
So we're assuming that the contestant chose door 1.
We're assuming, yes, thank you.
I'm sorry.
And thanks for pointing that out, Sue, because there's no loss of generality in assuming that the contestant chose door 1. What we could do is make the analysis more complicated by saying the contestant rolled a die to choose the door, but we would reach the same conclusion. So in this, as in many cases where there's a built-in symmetry of the problem, I will just say there's no loss in generality in assuming that the contestant has door 1. Now, let's identify some events, and this is going to be a little bit of a squeeze now that I've made this big table, but I think I can do it. So, here are the events. A equals car in door 1. It's really behind, but I don't have enough space to use the correct preposition. And B is that Monty opens door 2. That was like my ripping open a certain specific envelope. Okay, so we've got it. You're the contestant. You chose door 1. Monty Hall opens door 2. And now what do you have to calculate? You have to say, what is the probability that the car is behind my door given that Monty has opened door 2? And of course the answer is that's the probability of A intersect B divided by the probability of B. And looking at these 6 equally likely individual outcomes, what's the probability of A intersect B? Which is the only one of these that corresponds to A intersect B? The first one, right? This is the only one where the car is behind door 1 and Monty opens door 2. Which are the others that correspond to event B? 5 and 6. Okay? So you can say half the time he will open door 2. Right? He's going to open door 2 or door 3. And just on the basis of symmetry, the probability that he'll open 2 rather than 3 is 1/2. And the probability of the event A intersect B is 1/6, because that will happen in 1/6 the cases. So the probability that the car is behind door 1, given that he has opened door 2, is still 1/3. And in fact, that's perfectly obvious when you think about it. It's really hard to see how people get this problem wrong, except perhaps by misunderstanding the protocol. So what Robert should have thought, though he'd be $1 poorer if he had done that, is, look, I had 1 chance in 3 of having the dollar bill in my envelope, and the fact that Paul ripped open one of these rather than the other doesn't make a bit of difference. I've still got 1 chance in 3, and therefore, if I switch to the 1 remaining envelope, I will up my probability of having the dollar bill from 1/3 to 2/3. Yes?
You did say that there was a larger picture of Bush in the one that you were going to open. And that
But
might,
the
that might
two
have been-
pictures were about half a centimeter apart. If you are quite right, though, in your implication that someone who knows a whole lot about goats might, on looking at the goat, say, given two goats chosen at random, the probability that this is the larger of the two looks to me more like 64% than 50%. I think for that reason it's best for Monty to have a secret criterion for picking which door. Otherwise it complicates the problem. Now, here's another way of analyzing this problem. You are the contestant, and you've picked your door, and they break for a commercial. And someone rushes to you from off stage and says, "Psst, I've got a way you can do better. Look, you've got 1 chance in 3 of having that car. I'll tell you a way to double it if you pay me $50. Say, okay, that seems like a good investment. He says, look, there are 2 other doors. The car, if it's not, the car has 2 chances in 3 by the 2 chances in 3 of being behind one of the other 2 doors. Monty's going to open one of those doors, but he's not going to reveal the car. So all you have to do is agree in advance to take what's left, and you, get the benefit of both the other doors. That's a perfectly valid way to reason through this problem, and it also leads to the correct answer. Now, here's the most interesting thing yet about the Monty Hall problem. My friend Harry Lewis is teaching a core course called Bits on Information Technology in Harvard College, and he wanted to use the Monty Hall problem as an example in that course, and I think he may have wanted to put it in a book also. So he wrote to Monty Hall for permission. And he got a letter back from Monty Hall which said, "Dear Professor Lewis, I give you permission to use the problem in your book, but I understand that you've been giving the wrong analysis of the problem, and I want you to give the right answer when you explain it." And it turns out that Monty Hall himself did not know the correct solution to this problem. Monty Hall's letter indicates that he didn't understand that it was to the contestant's advantage to switch and raise the probability from 1/3 to 2/3. Okay, let me show you another sort of analysis of this, which is a little shorter. And let me also warn you, I think I am at present the world's expert in composing Monty Hall problems. You'll find one on the homework. You may encounter one on a quiz here or there. But the generic Monty Hall problem is, of course, there are n doors. Behind m of the doors are desirable objects. Behind the remaining n minus m doors are undesirable objects. Monty Hall opens 1 or perhaps more doors according to predetermined conditions, and then gives you the opportunity to make 1 or more swaps, and you have to decide whether it's to your advantage. And this is just the simplest of them, but once you understand how to do the simple one, the others are not significantly more difficult. So here's another analysis. This is a quicker analysis. And this is based on Monty flips a coin, by which I mean if Monty has a choice of doors to open, he doesn't choose the smaller goat or use some predetermined condition like that. He, in effect, uses a chance device to give himself a 50-50 probability of opening either of the 2 doors. So now we can simplify the 3 cases. So again, you've picked door 1, and the 3 cases are car, goat, 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 car, goat, 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 car. And now I have to tabulate one more thing. Let's see if red will show up tonight. Yeah. So I've labeled this last column Monty opens door 2, but it's really conditioned on this case. So this is going to be the conditional probability that he opens door 2 if this is the setup. And what's that?
50-50.
50-50. Because this is the one case where he has to flip a coin. He can open either door. What's the probability that he'll open door 2 in this case? 0. And what's the probability that he will open door 2 in this case? It's 1. And now the analysis sails through in exactly the same way. The probability that you got the car, given that he opens door 2, is the probability of A intersect B divided by the probability of B. The probability of A intersect B is 1/3 for case 1 times 1/2 for him to open door 2, exactly the same as before. And the probability of B is 1/3 for case 1 times 1/2 for him to open the door, plus 1/3 for case 3 times 1 for him to open the door. That's 1/6 or 1/2 or 1/3, same as before. Now, I have a significantly more complicated version of this, which I'd be happy to present for fun, but I think a higher priority would be to see, we've got 10 minutes left, do we? Whether there are questions I can usefully answer, both for the studio audience and the video viewers, that might help out with next week's quiz. I'll give you a minute to think about this. Something you'd like to have me explain again that would help out with the quiz. If there are no such questions, I will state the Christine random desserts problem and give you at least a partial analysis of it. No questions? Okay, so here is Christine's random desserts. I put this in the notes. It is the ultimate Monty Hall problem, but it's really too complicated to be worth the trouble. The claim I will make for this problem is that this is the first Monty Hall problem I've seen where you come up with a number for which I, at least, haven't been able to come up with a shortcut calculation. With the original Monty Hall problem, basically you can say, look, you got 1/3 of a chance of having the car. Monty's opening the door doesn't change that. And there are lots of variants where that's part of the answer, that the probability, the conditional probability that you've got the prize is unaffected by what Monty did. But this one is a little bit different, and I owe this to Christine Liu, who took one of my courses a couple of years ago, and who had the bright idea of bringing paper cups to demonstrate this. Alas, I have forgotten the paper cups, so I'm going to have to simulate them. Have people noticed the dessertery called Finale on Holyoke Street? One of Harvard Square's trendy spots. And that was the inspiration for Christine's random desserts. So here is the basic idea. In writing the placement test problems, I was taken to task for one of my reviewers for, I think, for using too many female names. They said this was condescending to women to use an unreasonably large number of female names. And so, I don't know, you probably didn't notice this when you took the placement test, but in all the placement test questions, there are two protagonists. they both have androgynous names, and therefore you can interpret this as a question involving a heterosexual couple, a gay couple, or a lesbian couple. All are equally valid reasons. They are referred to, of course, as they, so I never have to use he or she in the problem. So the Christine random dessert problem begins. Shay and Marty walk into Christine Random Desserts, Harvard Square's trendiest after-hours eating spot, and they ask for a table for two. Christine herself appears and escorts them to a circular table at which there are 5 places. In front of each place is one of those fancy metal domes that you see lifted in chic French restaurants. And they say to her, "Why are you giving us a table for 5 when there are only 2 of us?" And Christine says, "Well, in fact, under 2 of these domes are complimentary servings of my famous homemade cookies. Under the other 3 are crunchy veggie snacks. Here, want to see?" And knowing wits where, she lifts up a dome to reveal one scrawny carrot. And then she says, of course, "Would either or both of you now like to change places?" So you can work this out for your own entertainment. And it gets a little bit complicated. You can say, for example, if they both got cookies and they both switch, they both have carrots when they're done. And the case for which I can't find the shortcut is the probability that they will have cookies if one and only one of them decides to switch. The answer is correctly worked out in the notes, and if anyone can figure out a shorter way of getting to the same answer, you can email it to me. You can ignore this if you like, because it's overkill. It's just an example of the ultimate Monty Hall problem, which I thought you might enjoy. So, speaking of things you'll enjoy, I'll see you all next week, promptly on time for the quiz. And those of you out there in video land, remember, if you live in the New England states, you have to show up next week. I'm going to give out the next batch of handouts then. And if you don't live in the New England states, you need to get in touch with the Extension School and make your arrangements to have your exam proctored.